Hello. Hello, sir. Let us wait for 5 more minutes so others can join also.
Okay, but is my screen is visible to all?
Yes, yes, sir.
Yes,
It
sir.
is perfectly visible.
Okay, okay.
Hello, everyone. Let me introduce the next speaker, Dr. Subodh Kire, postdoctoral researcher, Raiken, Japan. Dr. Kire completed his PhD from Savitribai Phule, Pune University in the year 2016. Currently, he is associated as postdoctoral researcher with Raiken, Japan. His interest lies in enabling investigation with a handful of off-the-shelf hardware. During his postdoctoral work, he was regularly involved in developing, testing, and benchmarking the state-of-the-art software molecular tailoring approach (MTA), which is essentially based on divide and conquer algorithm. He has also authored 16 research articles published mostly in core journals such as JChem, Physics, JPhysics, Chemical, etc., as well as some invited contribution to the edited books. Edited books named such as Aromaticity and Metal Cluster, Atoms, Molecules, and Clusters. So now, Dr. Kire, uh, will present his slides. Hello.
Hi. Thank Ashish for the introduction,
Yes.
and good afternoon to everyone. Actually, this is very bad time to start with, especially after the lunch, and I hope I keep you all people awake, especially after the lunch time. Okay, so welcome all, and I thanks to everyone, especially to the Professor Gadre, because he has presented overall molecular tailoring approach in very good way, so that I have very limited things to share with you because most of the thing he has already covered in his talk. So I am Subodh Khire. Currently, I am working with RIKEN, Center for Computational Sciences in Japan. To start with, I just want to tell you one small thing about our institution here in Japan. It is one of the good institution in Japan. It's RIKEN, and most peculiarity, it is famous for the one of the largest supercomputer in the world called as Fugaku. And this Fugaku supercomputer computational facility is installed at our institution here in Kobe in Japan. It has several, rather few lakhs nodes available built by the company Fujitsu, and it is a very mammoth architecture available. And this architecture is also available for the researchers through collaborations. And there are a lot of several research groups are working in the RIKEN on using the Fugaku computational facility. Okay, with this introduction, I would like to tell you about a molecular tailoring approach, which was my PhD topic while I was working with the Professor Gadre, and I'm also pursuing the same field on the with the different topics and the different test cases. So at the back, the my talk overall my talks about I will talk about the why to tailor a molecule. Basically, what is the use of molecular tailoring approach and what is molecular tailoring approach? And as mentioned by Professor Gadre, it has utility for automatic fragmentation because for uninitiated user or very new user, the fragmentation is really a task. So for circumventing this, we have automatic facility with this. And with this MTA, how the geometry optimization works, I will tell briefly about that. And then I will also, not in detail, but I will just give the application of MTA to probe the hydrogen bond strength in molecular clusters. I think Professor Gadre has already covered this topic, so I may not talk much on this. And at the last, I will talk about some conclusions. Okay, so why to tailor the molecule? I think all of you here are now aware of that. For large molecular systems, applying the higher level of, rather I mean say, good level of theory is a challenging because increasing the level of theory, though augment the results, however, you will face a lot of challenges computationally. Means you need a high machines with a high configuration nodes. That nodes must be have the very good memory disk, and all these problems are come in front of when you are challenging it. And this level of theory again has to be executed with the basis set as per the definition of the things. And this basis set again another dimension which is increasing the complexity of the system. So just to highlight this, what happens with that, you can see in the first graph for the single for water cluster with n in the x-axis in the first graph, it is a number of monomers. You can see with the increasing level of theory from Hartree-Fock CCSGT, how exponentially time increases, means with the increase in the number of atoms in the case. And in the second thing, for a single water cluster, if I use the higher basis set like the augmented CCPV, double zeta, triple zeta, quadruple zeta, and how the time increases even for a single water system. And when you are executing this data, the level of theory means the method as well as the basis set, you can imagine how the system grows exponentially, and we need a very high dimensions. And all this, and as you all aware that we have limited computer science thing, means we have the limited memory, limited things. So at one point, using the any biggest hardware in the world, we are not able to do the calculations. But you can definitely anticipate from this scale. So this is the exact problem with the when you are trying computational problem, when you are trying to do the ab initio calculations on the large molecular systems. So, and from this graph also you can see, and Professor Gadri has also mentioned, it has the inherent scaling, like the Hadrey-Fock scale raised to n raised to 4, where n is actually the number of basis functions, and MP to a bit higher level of theory, and again it raised to 5, and couple cluster and all raised to 7. So overall, looking at this picture, while doing the calculations on large molecular system with reasonably large basis set and good level of theory, we are stuck and we are not able to do the things. And this calls for looking at new approaches in ab initio level of theory. And this was the motivation of why to tailor a molecule or why to fragment a molecule. And at last, as Einstein said, something are very easy to say but hard to do. Means fragmenting the molecule is easy to say, break the molecule and do the things, but they're a bit hard to do the things. So with this background in the literature, there are several literature can be available. There are a few research group across the globe who have developed the idea for circumventing this computational problem, and they use the fragmentation techniques into that. And molecular tethering approach is one of the pioneering work in this direction because it is instituted basically in 90s, 94. And later on, there are different groups are available. Now they are doing they are applying the fragmentation method for enabling the ab initio calculations on large molecular system. Essentially, all these methods follow the same thing. Take a molecule, break into the smaller things, apply the calculations on the smaller things are called as fragments, and patch the results back. But these systems differ in how they are defining a fragment and how they are patching back. This is the essential difference between all these fragmentation schemes. And molecular tethering approach since 1994, over the several years, it has got a lot of augmentation in the code, and now the currently available code is capable of doing very much things at all. So to start with a molecular tailoring approach, what we are doing is that we are cutting a molecule virtually. Virtually in the sense we are not cutting anything in vitro. This is a completely computational trick wherein we are separating the molecule on the basis of the distances. And now suppose this is the one test case I showed here. It is a water benzene molecular clusters. And as I took this example, it is easy to demonstrate because in molecular clusters, we are not breaking any particular bond. So it is very easy to understand. But scheme is easily translated to the any molecule, and we also demonstrated it effectively, and which I will show in the coming my presentation. So for a large molecular cluster, it contains the water molecule and a benzene cluster and benzene single molecule. So I cut it into the three fragments. One contains the water, another contains one benzene and a few water, and in it is an overlap of few water. And we are using the set exclusion inclusion principle, like the energy of the set of the union of two set is the value of one set plus another minus the intersection one. And you can see the energy. The intersection energy means that I'm talking about the full energy of the whole molecular clusters, and the energy of fragment 1, energy of fragment 2 minus the intersection 1. These energy numbers we are getting from the ab initio software running at the back end. And our software MTA is currently tuned with the Gaussian games up to some extent for the NWChem and Orca, but we are full-fledged for the Gaussian as of now. So we are, after virtual cutting the molecule, we are giving it to the ab initio software, getting the energy, and we are patching back the results by simple mathematical exclusion inclusion principle, and you can see this. And as you can see here, though it's a demonstration purpose, in principle there can be multiple fragments, not only limited to the two. Systems are, as per the requirement, one can fragment the molecule. And this is the example I'm demonstrating here for the energy, but certainly this example can be readily expanded for calculating the gradient and as well as the Hessian. So with the same equation, we can calculate the molecular properties. Currently, I'm showing as the energy, gradient, and the Hessian. And with this all, so what is the first step in challenging in applying the molecular Turing approach is the fragmentation. So what are the things in what are the prerequisites of the fragmentation? Uh, as I said, it's a virtual cutting of the molecule. So you can cut the molecule in numerous ways, means as per the thing. And during the talk of the Professor Gadre, someone has asked what is the largest or the minimum constraint on that. So with this question, I want to answer here is that basically you can make the fragment as large as possible, as small as possible, as per your ease. But however, it is the very tightrope act between the accuracy and the efficiency. If you are having the very big fragments, and of course your results will be very accurate, but the timing you may not be seeing very good. So you can make the fragment as large as possible, which is considering your hardware capacity. If your hardware is uh, strong enough to calculate the calculation on a one fragment, that much size you can do. And with this all background means, once you know the hardware capacity, what is your level of theory, what is the basis set, and what is your anticipated time for this calculation, if you what is your disk in your hand, considering this all, you can fragment the molecule. And once you decided, this fragmentation is nothing but art with a chemical intuition. So these are the only prerequisites for the fragmentation if you want to do it by yourself. But the thing is that we are already taken care of this problem, so that we can any new user can apply our software for their calculation, for routine calculation. So we have automated the things. So for fragmenting the molecule, it is available, fragmenter is available, and it is within the code. So you don't have to do anything. And during the fragmentation, this is the overall picture of the fragmentation. First, it will take the Cartesian coordinates of it. Then it will use some user-defined parameters as the rad cut and max size. Rad cut is nothing but the distance cutoff for generating the fragment. I will not go much into this detail. What is the rad cut and the max sizes? But right now, you can believe me that rad cut is one of the parameter. On that basis, uh, fragments are generated of this much capacity. And this is the unit in the angstrom, because our Cartesian coordinate are in angstrom. This is, you may consider it as a radius for generating the spheres, which is used for generating the fragments. And max size is the maximum number of allowed atoms in a fragment, and likewise the mean size is the minimum one. Once these parameters are is given by the user, the program will build the connectivity by using the information of the covalent and van der Waals radii of the atom, because that is already defined. Using this, the program will build the density, will find the distance matrix, and each know which bond is connected to which bond, and type of bond, using the bond lengths. Means it is single bond, double bond, or triple bond, or a weak bond. So it will identify this. And after identification, the program is also smart enough to identify the rings, means the whether this is a 6-membered ring or a 5-member ring, is a benzene ring or something like that. And once you identify the connectivity of the atoms, identify the rings, using the user supplied parameters as a rad cut and max size, the program will fragment the molecule for you, and will generate the generates the fragments for you, which is easily supplied to the MTA software and for further use. And there are some rules and regulations to which is developed in our group over the years. and this is already implemented in the automatic fragmentation scheme, means we are generally not cutting the multiple bonds like a double or a triple bond, or we are not even cutting the benzene ring, planar rings. And using this all do's and don'ts, the program, the MTA software will generate the fragmentation scheme for you, and it will present the fragmentation scheme, and which is further used for doing the calculation. So likewise, I'm showing here one demonstration purpose, and this is a folic acid. And during the practical session also, we are providing the Cartesian coordinate of this folic acid to you, and you can also see this. Now, suppose if I this molecule with me with the 51 atoms, and I want to do it's the property like I want to calculate this energy at a given basis set, and number of basis functions for this basis set is a Popal 631G star is around 646 basis functions. So you can see the energy, and by for a given fragmentation scheme is I have cut the molecule by using our fragmentation scheme for a given fragmentation scheme, and I'm demonstrating here the MTA energy. And you can see the MTA energy is very near to the actual energy, and which is patched by doing the fragment calculation, not the full calculation. FC refers to the full calculation. However, you can see there is a still difference between the in the third digit, means in the millihartry, there is a still difference of this. And then the in our group, thought was generated ki what to be done, means if I'm doing fragmentation and I'm still our energy number is found to be erroneous in comparison with the full calculation, and can we enhance can we reduce this error by doing some extra calculations or some smart way for that. And then while considering this, our most of the thing in our mind is that contribution of a long-term interactions we are totally missing out, because due to the fragmentation, fragments are totally independent to each other. Means once our fragments are generated, a subsystem from a parent system, once they are generated, they are running independently to each other. So the bond in the larger atoms, which are atoms which are spatially extended with each other, that interactions we are missing out, and that is affecting the accuracy of the MTA energy. And then to reduce this error, a new method called as a grafting procedure, we are calling it a GMTA. This method has been proposed for doing the things. And now here again say that the full SB is the small basis set. You can see the full calculation energy using a small basis set and higher basis set. The assumption in the basic principle of grafting procedure is that the error in the fragmentation scheme means if I fragment the molecule and calculated the energy, and I calculated the energy without doing the fragmentation, and there is a difference, but this difference is almost consistent irrespective of the basis set. Means if the energy difference between the one basis set is higher and the full calculation of the MTA calculation, and the another basis set, and if these basis sets are quite related to each other, the energies, the difference is quite constant. So you can easily graft this error to the higher calculation. Means suppose if I want to in the given case, my higher basis set is augmented CCPV DZ, which is a huge basis set. It's a double zeta basis set, and I will take a smaller basis set as like a 631G plus G star. So I will calculate the full calculation energy at lower basis set, keeping the level of theory same, and I will also calculate it's the MTM is the fragmented energy into that, and I will take a difference between these two. So in that case, you can see the difference is 0.001 around 2 millihartry difference is this. And if I graph this 2 millihartry difference, graph means I am talking about adding this difference to the MTA energy, means the fragmented energy of the molecule at higher basis set. Let's say in this case is augmented CCP with DZ. The energy is augmenting. It's like it is coming as good as the full calculation energy, and the difference between the full calculation and the grafted MTA procedure is minimizing. So this is a good approximation model for calculating the actual for approximation to the full calculation energy of the large molecule. And as per our experience, this runs very well for several molecular structures and molecular clusters. But however, for adopting the GMTA, means grafted assistant MTA, you have to do an overall overhead step of doing the MTA calculation at the appropriate lower basis set, as well as the full calculation at the low. This is an overhead of the computation. And with this, the next point I want to discuss is about the model geometry optimization, which is one of the feature of the MTA. And I would like to mention here is that within the fragmentation methods, there are very few methods which have actually implemented the geometry optimization. And MTA is one of the method where we have adopted the geometry optimization module in our MTA. And during the geometry optimization, what we are doing is we are taking the Cartesian coordinates and fragmenting into the molecule, and the fragments are totally independent to each other. That's why you can use any parallel method for this. We are calculating the energy and the gradient of the fragments. We are patching it back by using our set exclusion principle, and we are putting the constraint on this energy gradients, the threshold. If the patched energy and the gradients are up to the threshold, means cutoff decided by the user, it will stop the geometry optimization. Or if it is not, again it will this energy gradient and the Cartesian coordinates of the molecule, it will given to the any optimizer. Right now we are implemented with the LBFGS geometry optimizer because this is the freeware and available in the literature. And of course, there are several optimizers we can definitely employ at the backend using the MTA. And we have used the LBFG available right now. This will be given to the optimizer, and again optimizer will give you the new geometry using the gradient and the energy, and likewise the geometry optimization module process, and the job will stops when all gradients and the energy are below the cutoff. The geometry is not moving much if the gradients are too small. And recently for molecular clusters, we have adopted the Bernie algorithm, which is implemented in Gaussian and which is supposed to be very good. So recently we have uh, able MTA, our MTA software, to tune with the Bernie algo, to tune with the Gaussian Bernie algorithm, and we can able to do the geometry optimization using that. Here, few points here I would like to mention here is that during the fragment calculation, fragments are never fully converged because for each cycle it is calculating the energy and gradients and patch for the parent molecule. And parent molecules, the cutoffs are checked to be checked on the parent's molecule and not on the fragmentation, not on the fragments. Second thing is there, in principle, any ab initio package can be employed at the backend because MTA is independent of the ab initio theory level of theory and basis set, because it is borrowing the output from the ab initio calculation. So in principle, any ab initio calculations can be employed at the backend. And more advanced software optimizers can also be employed, and we are currently we are tested with the Bernie, which I just now mentioned. With this all things, we have done some MTA benchmark optimization for the water clusters, and you can see the 7 low energy isomers of water 25 clusters, GMTA versus full calculation. And in the below we have I just want to mention highlight the hydrogen bonds. The average distance between the hydrogen bonds between the full calculation optimized geometry and the MTA geometry. So we can see it goes in very good way. So means the geometry obtained by using the MTA and the geometry optimized by doing actual full calculation with the very huge architecture, and you will end up in the same geometry. That's the message I want to give here. Means though we are following some approximate path, and finally we are landing it with the same geometries which are supposed to be using the large molecular clusters. And with this molecular cluster, I just want to demonstrate here we have capability that our software we are also benchmark for using the basis set like a QJ augmented CC3V QJ basis set, which is a very large basis set, and we are able to calculate its energy even a very minuscule architecture. Means you can see for water 16 for 2007 2751 basis function is MP2 theory. We are using this only 16 core machine, and even we are also able to use the core i7 based machine for this calculation for around 7000 basis functions in the case of one YJP, which is small protein. So this is the beauty of the things. In the large basis set, also we can able to do the calculation even in the off-the-shelf hardware. You need not to do on this very high-end machines. So MTA features are these are very minimal use of MTA keywords because most of the MTA are programmed. So as a user, you don't have to worry much apart from you just have your Cartesian coordinates in your hand, and you have, if you already have a fragmentation scheme for that, you can use that as well in the MTA. Otherwise, you can take the help of the automatic fragmentation scheme available in the with the MTA. You can also take a use of that. And MTA is adaptive in nature. So as I mentioned, any ab initio code can be used. And these fragments are totally independent to each other. So they are highly parallel and ready to use on HPC platforms. And we have tested our MTA software on several NSM machines like Param Shivai, Param Yuva, Param series, lot of things. We are already demonstrated and our software on the large HPC machines. So applications of MTA to the large molecular cluster. One more thing I want to tell you that this is the application for the large molecules. So if you are trying to use the MTA for very small molecule, you may not see the results very good. Or contrary, you may find the results worse for doing the full calculation. So this is the MT calculation is useful when you are trying to do a large molecular systems with limited hardware and the ab initio. In that case, you can really see the magic of the system. So our MT is unable to calculate the energy gradient, and of course that's why the optimization with computational economy. Construction of the density matrix, we can able to do the density matrix for large molecules, which can be a very good guess for doing the further SCF calculations. And I hope most of the people are here aware that guess to the density matrix is a very crucial step in the SCF procedure. And for the large molecular systems, by using our application, we can generate a good density matrix, and we are developing positively on this front also. And building the Hessian matrix and predicting vibration spectra, this is also there. And of course, the Dr. Sahu will talk much on this. He has expertise on that section. And the MT has also been employed for calculating the intermolecular hydrogen bond strength as well as the cooperativity. So the software is already there in the literature. You can download it or you can ask us. So at the last, I would just like to highlight the which research themes we are currently pursuing with the MTA. So the first theme is the construction of the CCSDT level potential energy surface. Professor Gadre has already talked about that. We have successfully shown that this our scheme, means MTA model, is able to calculate the potential energy surface at the CCSDT level for a couple of molecules we have demonstrated. One is a topolon and another is a different another one. So two molecules we have demonstrated that our method is effectively work for generating the potential energy surface, and we have published this paper on this. In the similar way, we have also generated the potential energy surface, means the CCSD level investigation on di and tripeptide. And dipeptide were already published, and we are making some good progress on tripeptides, and hopefully we are able to get some good results in tripeptides. But yes, for dipeptides, we are already demonstrated our software. Third is the IR spectrum and the molecular cluster is another very big stream for doing the ab initio calculations. Sahu will talk much on this one, but yes, we are also done a lot of things in this. And we are also applied our software for even for the proteins. Someone has asked that. And the last thing we are exploring is the applying the MTA method for calculating the strength of a hydrogen bond. So there are several papers in this group also. This work was in collaboration with Dr. Milind Deshmukh from Sagar University. Basically, he instituted the idea in while working with Professor Gadre. And, now we have published our paper, and the program is also available in the literature, and which is available for the use. And in the fifth theme is we had while working with CDAC, the CDAC team has a very good application calling as a PSE, means the means the problem solving environment. And the beauty of that software is that it is enabling the scientific applications on HPC machines. And because, as I mentioned, that key MTA maybe find troublesome for the new users, because the users may not have the expertise in using the HPC machines or fragmentation or doing the calculation. So with this, we quickly understand that this problem solving environment can be of use to us. So we have, in collaboration with CDAC team from Mr. Shankar, Mr. Kedar, Dr. Kadam. So they have come up with a nice idea that why not to integrate our software in the backend, and in the front we are developing the problem solving environment, which is the web-based utility. For a new user, it is very useful for using the for using the things. And this is also done, and which will be demonstrated here. Means in this session, you are also using this GUI development for HPC for this workshop. And MTA technical prerequisite is very limited, and I want to tell you that MTA can be accessible in two ways. First one is a command prompt, and another is the through the PES, just now I mentioned, which is a utility developed by the CDAC team. However, most of the feature are yet to explode using the PSE, but our command prompt systems are ready to use by any user, and it is already installed on the NSM clusters, so we can all use that with our collaboration and with our help, minimal help. But once you got installed, once you hand expertise in using it, you can use independent to ours. So it is a very modest requirement. Software front, you need a Fortran or Python libraries. At the right, the Gaussian suite of software. And if you want to use the parallel environment, you want the passwordless sessions to the computer is the parallel mode. And of course, in the chemistry front, you should need the XYZ Cartesian coordinates of the molecular system. And fragmentation scheme, it is available already at your disposal. You can use that. Otherwise, you can take the help of the automated system. And the level of theory means small and large basis that at what level of theory you want to do the calculations. And then the MTA keywords means what do you want to do, means MTA energy or IR or the Raman. With this background, you can submit the job and take a coffee break. So these are my conclusions. In general, MT offers a solution for non-linear scaling problem of ab initio methods, and most essentially using the off-the-shelf hardware and with drastically reduced time. As Gadre sir has already mentioned in his talk, how good it is. It is very reliable in accuracy wise, because we are able to calculate the energy of a system within the 1 kilocalorie of a mole, which is having the chemical accuracy well accepted one is substantial reduction time. With the utility, it is used in the various systems demonstrated for density matrix, IR spectra, molecular orbitals, hydrogen bond energies, even the molecular electrostatic potential, molecular density, scalar fields like this. And it is adaptive in nature, no level of theory and the basis set and the background program technically. And with this background, we are working on the open shell systems, excited calculation, and hydration of the molecular system. So, and like the last, the take home message for everyone that molecular tailoring approach is a model wherein you can do the ab initio treatments like the property calculation and the IR and vibrational IR and spectrum of around 1,000 atoms for Hartree-Fock and the DFT level, 300 atoms on MP2 and 1,000 atom at CCSD or CCSDT. And of course, these numbers are not fixed, means it can be definitely changed as per the requirement and all. But this is what we have benchmarked. That's what I want to say here. But if someone has having a particular requirement or he has some particular interest in doing the things, yes, we can definitely apply the molecular tailoring approach for their system. So at the last, I would like to thank you to the Miss Nisha, who is a coordinator on this workshop. Computational time and technical support from National Supercomputing Facilities, Param Shivai, Param Parul, and Smaral Pruthi. And I troubled them a lot for asking a lot of questions and needing the computational nodes and all. And I also like to also thanks my a team of MTA, means my seniors who has given me the good knowledge about the program and all, and I can do the things. And last, I would also like to thanks to my present institution, RIKE. Okay, so this is what I would like to stop it here. But during the practical session, we are also I am also demonstrating how to use exactly what are the more technical details, what are the output, and how to interpret the data using the MT. I will show into this. And for any oral query or collaboration, please contact to Professor Gadre especially. Of course, I am also there. Nityanand is also there. But for oral query, you can contact Professor Gadre. And if you need any technical assistance or if you want more details about the program and how to use and something, then you please approach to us. Our email IDs are given here. And please do contact and please interact. And yes, and more about during the practical session. I'm also there with you for the whole day. And I hope you will enjoy that session also. Yeah, thank you.
Thank you, Dr. Kire. If anyone has any question, you may ask. Okay. If there is no more question.
Okay, I think okay, I think everyone is left. That's not my main question. That's not my main worry after the lunch. Okay, anyways, just kidding.
Okay. So our next speaker, Dr. Nityananda Shahu. Dr. Nityananda Shahu completed his PhD at IIT Kanpur in theoretical and computational chemistry under the supervision of Professor Sridhar Gadre in 2016. After his doctoral study, he moved to Germany for his postdoctoral research. From July 2016 to September 2018, he was working on the semi-empirical method development with late Professor Alter Thiel at MPI Coal Research in Melham, Germany. Later, he moved to University of Marburg in Germany to join Professor Robert Berger Group. During his stay at Marburg from November 2018 to August 2023, he was working on electroweak quantum chemistry and parity violation in chiral compound. Since September 2023, Dr. Shahu is working as assistant professor in the Department of Chemistry at IIT Jammu. His current research interests include electronic structure calculation of large molecular systems, development of fragmentation technique in quantum chemistry, vibrational spectroscopy, quantum tunneling, and parity violation in chiral compound. Okay, over to Dr. Shahu.
Okay, am I audible to all?
Yes, yes, you are audible.
Okay, so thank you, Paramita, for a lengthy introduction. Okay, so good afternoon to all, and I will talk about MTA spec software, which is an outcome of MTA actually. So most of the things are already described by Professor Katre and Dr. Khire. So my job is now very easy. So I have very little things to describe. So maybe I will go fast, but anyway, we have enough time. So as you already know that MTA is a fragment based method, and we do fragments, then we do the calculation. So this is all already known to you from the previous two talks. So we have many parameters, and there are many utilities within MTA to enable calculations. So currently we enable energy gradients, and then the vibrational IR and Raman spectra, and of course the geometry optimization of molecular systems, which includes both molecules as well as molecular clusters. So what is MTA? And then again, I'm repeating the things. Calculations are on fragments. So due to the fragment based calculations, the computational complexity that is reduced to the fragment level from molecular system level. And that is why we can use, or we can do large system calculations uh, using off the shelf hardware. So MTA basically provides you the feasibility of doing the calculations. So in general, the where the conventional calculations or the conventional programs fails, MTA starts its work. So with MTA, we can do actually large calculations on small hardware. But let's talk about what about the accuracy of MTA calculations. Feasibility is okay, we can do the calculations, but what about the accuracy of the outcomes which we get after the MTA calculations? So as we have been saying that MTA is a method which does the calculation on fragments rather than the whole system. That is why it is an approximate. And being approximate, the result which we get from MTA should not match with what we get from the full conventional calculations. So that means the MTA properties always carry some error when you compare your result from MTA to the full calculations. And during the post-Hartree-Fock methods, it has been already observed that the large part of the error comes from the Hartree-Fock level. And the most interesting notification here, for a given system and for a given fragmental scheme, the errors of MTA with respect to the corresponding full calculations are almost basis and independent in nature. And this fact we have been using now to correct the MTA based properties, and we have to and we are able to get a better accuracy when we use the basis set in nature of the errors within MTA. So what does that mean? So let's say you have a system, you have a given system, and you have a given set of fragments. Now what you do calculations at a detailed level of theory. Let's say talk about MP2 theory, and you have three basis sets. Let's say one is very small, lower basis, and there is an intermediate basis, and there is a higher basis. And you do, if possible, you do full calculations on the system, and they do then do compare the MTA value with respect to the full calculations at respective level of theory. That means at respective basis set. What you see in the left side, it is the lower basis set, and the blue ones are always our MTA calculation, and the red one is the full calculation. And delta LB is what the error in our MTA based calculations with respect to the full calculation at the lower basis. Similarly, we have delta IB, that is error of MTA with the intermediate basis, and delta HB, which is the error in MTA calculations with respect to the full calculation, are using the higher basis. So you can easily see that delta LB, delta IB, and delta HB they are very, very, very close. Okay, so that means although I am changing the basis set, but the error almost remain a constant. So that helps us to calculate the properties within MTA at a higher basis. How? Let's say we are very keen to do a calculation at the higher basis, and then you do the MTA based calculations, and you get the right blue box. Okay, but you can do the full calculation there. Okay, so you don't have any idea how good or how bad is my result from the MT based calculation. But what you can do, you can always do a full calculation at the small lower basis, and also do a MT based calculations at the lower basis. Remember, I am talking about the given scheme and given system. Okay, so once you do the calculation MT and FC at the lower basis, you take the difference and you just add that to what you get from MT based calculations at the higher basis. And since delta LB and delta HB, they are very, very close. So once I take delta LB and add to the MT based calculation at the higher basis, it will be very, very close to the full calculation. Okay, that means when you add this small error, or when you grab that small error from the lower basis to the higher basis, your result is now very close to the full calculation. And this is how we can always minimize the error. And the procedure is called grafting procedure. Okay, so I will not go into details, but as I said in the previous slide, since the Hartree-Fock gives more error, the large part of the error in the MTA calculation comes from the Hartree-Fock. We do avoid the Hartree-Fock calculation from MTA when we do the post-Hartree-Fock method. So we do separate the Hartree-Fock part and the correlation energy part. Then we do many things. Finally, we will able to get the grafted energy, which is very, very close to the conventional full calculations. So this is the table shows the accuracy of the MTA and the GMTA. GMTA means the grafted MTA after having all the corrections. So there are various systems tabulated here, and then the corresponding basis set, which shows how expensive or how intensive is your calculation. And all these calculations are done at MP2 level of theory using augmented CCP VTJ level of theory. So for these calculations, augmented CCP VTJ is my higher basis, and I used 61 plus G star, the lower basis. Okay, so the third column in the table that shows the difference of the MTA based calculation with respect to the full calculation, and they are all in milliarity scale, that is 17, 19, 18, it so goes like that. And once I take the error which we get from the lower basis, smaller basis, lower basis to the higher basis, okay, then the look at the results which is shown in the fourth column. Now the error are in sub-millihetry scale. And remember, 1 millihetry is already 0.6 kilocalorie per mole, which is well within the chemical accuracy. And when you achieve a sub-millihetry scale, that means your energy is bypassing the full calculation. So you don't have to do or you don't have to concern about the full calculation, the feasibility or the accuracy. You just do MT calculations and do the grafting procedure, and surely your numbers will be bypassing the full calculation numbers. Okay, similarly, we can do many things. We can always increase or enhance the basis sets or level of theory. So like once you do the augmented VTZ, you can go to a triple zeta, then you can go to the quadruple zeta, and so on. And ultimately you will be able to get the estimation for the CBS level. Complete basis limit is also well within our reach, because there is MTA grafted energies, they are very accurate as compared to the full calculations. once we have the grafted energies, then we can always calculate the CPSE limit very accurately. Yeah, so this is true again for CCRT level of theory. So what we did for CCRT, we initiated at MP2 level of theory. That means the MP2 and level was our starting point for CCRT level of energies. And again, when you do a CCRT calculation, MP2 energy is free. Okay, so wherever in this small equation I put MP2 and CCGT, you don't have to do two calculations. You have to do only one calculation and both will be coming there. Okay, so in this way, we can also minimize the error in MTA energies, which is coming from CCD table of theory. And in the table, you can see for four isomers of water cluster, two for water 16 and water 17. And the second column shows the error of the grafted MTA energies with respect to the full calculation energy, which is already available in the literature, and it is it is in the sub millimeter scale. Okay, and which is actually all zero in chemistry. That means the grafted MTA energy is actually replacing the full calculation energy. So there is no need to do the full calculation. Anyway, that is not possible by us, or even for the large computational facilities. And also when you are within the grafting regime, you don't have to worry about the accuracy also. The grafting correction takes care about the accuracy. So just to mention, it is the repeat what Professor Godre also said, that people have been using very large lakhs of processors, using lakhs of processors for doing these type of calculations. But we hardly use 40 or 50 number of processors or single desktop machines, or even if you have a good laptop, you can do these calculations on your laptop. This may take some time, but this is all possible. And along with the feasibility, the accuracy is also warranted here, because we are minimizing the error from the grafting procedure. So this is all about energy. So now we can go to the spectrum part. So following the success of grafting procedure for energy, in calculating very good energy within MTA procedure, we thought about the frequent vibrational IR and Raman calculations. So for that, what we need? We need three properties. One is the Hessian, which is a double derivative of energy with respect to the coordinates. And then we need dipole derivatives, and we need polar derivatives for the calculation of IR and Raman spectrum. So when you have your Hessian matrix, what do we do? We do Hessian calculations on each and every fragments. Then we patch the Hessians, the dipole derivative and the polar derivatives for each of the fragments to get an estimate for the Hessian matrix, dipole derivatives and polar derivatives for the whole molecule. Once you have the full Hessian matrix for the molecule or for your molecular system, then you can always, there is some mathematics, you can always get the IR frequencies, or you can get always the eigenvalues of the Hessian matrix by solving the eigenvalue equation. Okay, so remember the eigenvalues of the mass weighted Hessian are nothing but the frequencies which we get from the normal calculations. Okay, so once you have very good Hessian, obviously the eigenvalues will be very good or very accurate. Then our frequencies will be very accurate. Okay, but again, since the MTA is an approximation, so the Hessian matrix which we get from the MTA based calculations are possessing some errors. So we want to minimize that error again through the grafting procedure, like we did in the energy. Similarly, we can minimize the errors in the dipole derivatives and the polarity derivatives, which we get from the MTA-based calculations using the grafting procedure. So we do multiple steps calculations with two different basis sets, larger and smaller, and then we do the grafting procedure to get a very good Hessian matrix, a very good dipole derivative elements, and very good polarity derivative elements. Once we are having all those electronic properties in accurate, manner, then we can always extract the information from those, and we will get the vibrational frequency and subsequently the intensities. Okay, so the Hessian matrix is directly related to the frequency. The dipole derivatives are um, responsible for the higher intensity, and the polarity derivatives, these are tensors all. Okay, and this is a triple derivative, so that is why the Raman calculation is very time consuming. Okay, so from dipole derivative we get higher intensity, and the polarity derivatives we get from the Raman intensity. And once we know the intensities and then the frequencies or the normal modes, we can always plot our spectrum. So these are the few mathematics, and this is all available in a very good book by Cross and Wilson. The title is Molecular Vibrations, the Theory of Infrared and Raman Vibrational Spectra. Okay, so the main purpose of grafting is depending upon the fact that we have already seen in the energy, that basis set independence. So what I just mentioned in that dashed box, these are the error of the Hessian elements and the dipole elements with respect to the full calculations at respective basis sets. Okay, and you see in all these three columns, okay, the numbers look very similar. Okay, so if you are also, you can check with the every TGR basis set, the number also very similar. So the errors are basis and independent. So once we have, let's say, the delta value at 631G, we can always add that number to the Hessian elements, to the dipole derivative elements, which we get from augmented CCP to get the grafted values for the Hessian elements and the dipole derivative elements. Once the error is minimized, we can do the accurate vibrational spectra analysis for our molecular system. So the error reduction after the grafting correction goes up to 0.2 percentage, and dipole derivatives goes 2 to 3 percentage, and polarity derivatives they goes up to 5%, but they are very less. We are more focusing on the Hessian elements because they give exact the peak values. Okay, so once you are having a very good Hessian and a very good dipole derivative elements and very good polarity derivative elements, then you can plot your spectrum by using the normal mode analysis. So this is again repeat. So on the top, just simple MTA calculations, which is in black, and the red one is full calculation. You see, they are not matching. Somewhere, so, on few places you see they are matching, but in most of the cases they are either red shifted or blue shifted. Also, their intensities are not matching. But when you go to the bottom two figures, you see the blue, which is the spectrum we get after the grafting correction, and the red one is obviously the full calculation with which we are comparing. They match with each other. So this is how the grafting procedure enables you to get a very good IR spectrum, which is almost indistinguishable from your full conventional calculations. And time wise also you have advantages, and as the system size grows and with the advanced level of theory, the advantage in the timing is also increasing. Similarly, this is the comparison of the full, which is red, and the blue one is our grafted MTA for two isomers of water 25, and you see how good the GMT spectrum with respect to the full calculation. Okay, and unfortunately, we can't do the full calculation, so we took help from US, and the blue one, which is the GMTA, we did by using our simple i7 based machines containing only 16 processors. Okay, but the accuracy is not missed anywhere. Yeah, so those are all about the clusters. Now we can go to our real systems, to the biological systems, which are mainly the polypeptides, proteins, um, and some other antibiotics or other molecules. So I'm just giving the comparison of our GMTA, that is the grafted MTA, with respect to the full calculations. And the blue one is our GMTA spectrum, and the red one is the FC. And if you just see the top two, I don't think we can see the red one. And the middle one, there is the intensities are varying, but the peak positions, they are well reproduced. So the GMT spectrum is indistinguishable from the full calculations. That means we can always bypass now the full calculations and go with the GMT, which is accurate and which is also very cheap to do. And we all can do in principle. And this is a spectrum comparison for a real protein, TRPG2, which contains, I think, 207 or 8 odd atoms. Okay, the upper one is the IR spectrum, and the lower one is the Raman spectrum. Okay, so the peak positions are well reproduced, except there is a NH stretching group in the NH3 plus group. The error, this is the maximum error so far we have found, is 8 centimeter inverse. For other people, it is also, they make it 0, but for us, this is very large. And it is due to maybe the charge center. Otherwise, all other peaks, including the peak positions and as well as the intensities, they are well reproduced. Similarly, this is another antibiotic, 3 conformers of gramicidin, which is a deca polypeptide. So the left one is the IR spectrum, and the right one the Raman spectrum for all 3 polypeptides. And you see the GMT spectrum is well reproduced as compared to the FC. So the bottom line is that we don't have to do any full calculations, because the GMTA or the grafted MTA takes you to the periphery of the full calculations. And you don't have to worry about the accuracy, because accuracy is maintained, and this is due to the error minimization in the MTA properties. Okay, so this is the story about the MTA development. We have MTA, which is based on the fragment calculations. That is why feasibility is warranted. And GMTA, which is a add-on to MTA, by adding the errors in the lower level calculations to the higher level, that is called grafted MTA, and it guarantees you the accuracy of the calculations. Okay, and then the next development is MTA spec, which is actually a software already available in the public domain that uses the utility of MTA and GMTA. That means MTA spec gives you both feasibility as well as accuracy in doing the high level calculations of large systems using very less hardware. So this is our MTA spec software, which is available in the link which I have put on the slide. Okay, and anyone can download the whole package from there and use for enabling large the calculations on large systems for the energy as well as the vibrational IR and Raman spectrum. Okay, so for that only you need a Linux based platform and some key based software. It is a keyword based software, and obviously right now we are using Gaussian software at the back end of MTA software. So once you have Gaussian and then Linux based machine, you can always use the software. And right now it does the single point energy, IR spectrum and Raman spectrum calculations for any molecular system, molecular measures at any level of theory. And accuracy wise, irrespective of the intensities, the MTA spec software could able to reproduce the peak positions of the spectrum to well within 4 centimeter inverse. And when we talk about the energy, 1 millihatry energy is all the error less than 1 millihatry is always guaranteed. Okay, so with this, I can summarize that MTA offers a solution for non-linear scaling problem of happiness methods using off-the-shelf hardware, and this is because we do fragment-based calculations rather than the full molecular calculations. And GMTA, which is a systematic approach for pushing the boundaries of high-level happiness calculations, and MTA, as I said, it does the feasibility, and GMTA provides you the accuracy about your properties. And there is no bar basis, no bar on the basis sets level of theory and the backend program, the MTA spec. And with this, I think I will stop here, and I should thank you for all attention.
Okay. If audience has any question, you may ask. I think there is no more question. So our next is our hands-on session. So
Yeah.
this hands-on session will be taken by Mr. Kedar, Mr. Shankar Nayak Rathod, and Mr. Ashish Nayak. Mr. Kedar Gokhale has been employed as a scientist E at ESEG Group, CDAC, Pune since November 2007. His areas of interest include digital image, video processing, machine learning and deep learning, evolutionary computing, object-oriented programming, and parallel computing on a high-performance computing system. Mr. Shankar Nayak is a scientist D at Center for Development of Advanced Computing, CDAC. With 15 years of extensive experience in research and development, Mr. Rathod specializes in computer vision, artificial intelligence, and deep learning. He has played a key role in formulating R&D proposal, co-authoring numerous research publications, and filing a patent in the field of machine learning and deep learning. Mr. Ashish Nayak is a project engineer at the Center for Development of Advanced Computing, Pune. He is working for the project Material Science and Computational Chemistry under NSM. He is actively involved in parallelization and optimization of code on multi-node system like Param supercomputer. Over to Mr. Nayak.
Thank you for the introduction, ma'am. So now we will proceed with the hands-on session. So for this, first I will show you some PPTs, and then after 10 minutes, I'm going to present you, uh, show you how to submit the job through PSC on our system. So for the PPT, let me share you. So yeah, basically it's problem solving environment for MTA spec software. So what is it? Problem solving environment is a web-enabled interface. It's basically a web-enabled interface to through which you can submit your job through any of the Param-based system which we have enabled, and we have enabled you to execute your job through those that environment. So now I will show you how your job is getting submitted through the Param system through our UI. So basically, this is the architecture of the MTA PSC. So basically, as you can see here, there is a web browser. So you will get a site through which you will get the site of the PSC through which you will submit your job. We will give you an input file through which you will just click on some steps, 3 to 5 steps, and after that your job will get submitted. The job will be executed on the param based system, which in this case it can be any of NSM clusters. So in our case we are using the param siva and param smriti system, which you don't have to know. So basically you can submit the job even if you don't know how to anything the parallel programming and any of those. You just have to have the XYZ file or some fragment file, and after that you can basically go through the steps and submit the job, and it will give you your necessary job execution and other thing. So now the next. So these are the functionality of the software. So first, we have already given you a user ID and password. So these are the basic steps where you first you go through login. Then if you want to see your profile, then you can go and see your profile. And then you will move on to the job preparation and visualization of the molecules. And after doing that, you will go to the submit job, and after submitting the job you can see your job status, the job management, and you can see whether you have to resubmit the job, you have to cancel or delete. And after completing the job, you can also download the output on your system. So this is basically the home page of the site. So this is the site we have provided to you. This is the link you will click and go to that site, and then you will submit the job. So I will basically simply go through the steps, and as you can see here, and after the PPT is over, I'm gonna give you the hands-on demo how to submit the job through the site. So through PSE you can submit the job and see the out. So here it is the PSC home. So basically this will the first page which will be open to you. After clicking on MTA login, you can log in. This is the page it will appear to you. So we have provided you the basic username and password. So you will enter the basic username and password and then the captcha, and then you will click on the login button, and it will log in you to your profile. Here you will get your profile. So after getting this, you have to click on submit MTA jobs. After submitting MTA jobs, you will go here and you can see all these options. So there are basically 5 to 6 options: level of theory, types of basis set, lower basis set, higher basis set, task names, grafting, non-grafting, upload input file, and display, and all these. So after this, these are the molecules we will take. So I'm going to show you basically 2 molecules, how to submit job through them. So here it is ALA molecules. This will be our molecule 1. And then I will show you molecule 2. That will be the folic acid molecule. There is an XYZ file and .list file, which we have also given you the link to download. So if you have downloaded it, you can see basic structure of the file. So here is the molecule 1 files. ALA molecules. These are the options you have to fill in when you are choosing this. So you in ALA molecules, you can choose MP2 turning. In the basis set, lower basis set, you can choose CCPVDZ, and higher basis set, you can choose these options. And then you can choose grafting or non-grafting. For the molecule 2, you will choose MP2 people and 631Z, and task name as single point energy, and grafting or not grafting. Same thing for this. So after doing this, these are the steps. After doing this, all this, you will see something like this. So after doing this, after uploading, you can click on the display button as shown in the arrow. So after display button, you will click, you will get a molecule figure. As you can see the 3D visualization of the molecule. And after you can see that, you will click on the fragmentation. So after clicking on the fragmentation, you can see the fragmented molecules here. And after seeing the fragmentation, 3D visualization of the fragmentation, you will click on the submit button. After submitting the button, you will go here. This is our job submission page. To the NSM cluster is going the job. After clicking on execute job, your job will be submitted with the following input parameters, as you can see here. And after doing this, submitting the job, you will again go to the PSC monitor homepage. And after the homepage, you can go to MTA job status. So this is our status switch to take the job status. Here you can see whether your job is completed or not. So this is the one of the page that will come if your job is getting submitted through the page. So here the job is being submitted, and after if your job is completed, then you can see the job completion status, and it will give you what amount of time. In this case, it was like 5.98 minutes. The job has been completed. And then you can also download your output file by clicking on it. So here mine was this. So after this, you can download your files. So you can download it. And these are the output files that you will get. Here one is attached is like output file of 100.out and the job.out I have displayed in the PPT. And thank you. So basically now I will show you how to submit the job through PSE. So
Just a minute. Just a minute. Yeah. Here, few point here. He showed some molecule file into that. Ashish, can you open that file, that lr2.xyz file? That can we go to the slide? Yeah. Okay. So here, these are the Cartesian coordinates in angstrom. Okay, so this is one of the important thing I want to mention here. When you are doing the calculation, you need a Cartesian coordinate of your molecule that should be in angstrom and that should be in XYZ format. Is anyone is here who do not know the XYZ format? Okay, I think no one has raised a hand. So I assume everyone knows the things. And second thing is that it is in the same slide, it is shown the fragmentation list file. But this is the fragmentation file which we have pre-run for you. Means it is not necessary that you should only use this file. You can use fragmentation file of your choice. But only thing is that that should be in proper format. And the format is here. I will explain you format if you need someone else. But for this session, we are exclusively using the fragmentation files which were already created for you. Okay. Yeah. Thank you.
So now we will move on to the job submission page. So let me open my browser. So I'm using Mozilla Firefox, and we have sent you the link uh, for the site. So you can go here, and this is our page, MTA login page. As you can see here, now you have to log in. You have to enter your user ID, which we have shared to you, and your password, and then the captcha. This is our login page. And after this, you have to go here, submit MTA jobs. So here, we'll do the first one, ALA molecules. So you have to choose MP2, turning. single point energy, and then you have to upload a fragmentation file, and then the XYZ file. You can choose grafting or non-grafting. I'm choosing the grafting one, and it will say your validation in progress. So it will take 1-2 seconds to do this. Now, as you can see, it is displaying the molecules. And after this, you will click on fragmentation. After fragmenting, you can see here the fragmentation of the molecule. And after doing this, you have to click on submit. So now we are in the job submission page. As you can see, it is submit job. And after this, you can do execute. So now your job has been submitted with the following input parameters, as you can see. Now from here, you again go to the MTA home, and then you can check your job status. So I have basically done this job. So this is our latest job, 25, 25th July and 3:24. We have submitted the job, as you can see here. So from here, you can check the status of your job. It takes some time to open it.
Meanwhile, do anyone have any question?
Now, as you can see here, your job is being submitted. So once your job is submitted, take some time. You will get an output. So if you want to, I have already done some jobs. So if you want to see, you can see I have already run this job. So you will get something like this if your job is has completed. So you can see here, it takes this amount of time to run the job. So once the job is completed, you will get here this option. You will get these options, and then you can click on here, and you will get the download page where from here you can download the job. So you will click on it, and I have already downloaded the job. So here is the your out file. You can see it. These are the things you will get. So these are the files you will get. So we can go to the MTO one, and this is the job we have submitted. We will check again. Until this job is going on, let's go and submit the job for our folic acid molecules. So we will choose this for the folic acid molecule. We will choose
Just a minute.
this.
She's just a minute. Actually, a thing is that we are already submitted one job for one of the molecule. Is anyone understand what is going on here? What is mean by basis set and how what are the choosing the parameters here? And as I already mentioned, we have a lot of another things which are available on the command prompt things, but through the PES, we are enabled only the single point energy calculation. So if you click on the task name, can you click on there, Ashish?
Yes.
Okay, so currently we are enabling the only single point energy calculations. We are not showing the job for calculating the vibrational IR and vibrational Raman because due to the time constraint. But definitely that is available in the software. Even the geometry optimization we are not demonstrating here. So you can able to show only one point at this for this workshop only. So if someone is interested in the vibrational calculation or want to see the output of vibrational spectra and how to do, please contact us separately. Okay. Yeah, thank
Sir,
you. Please
Pooja
proceed.
has some question, I think. She want to get addressed.
Sorry,
Pooja has some question.
Pooja.
So,
Okay, please. Pooja, can you please ask your question? I'm not able to hear you.
she is in the chat box, sir.
Is she not able to talk?
She is trying to type something on the chat section, sir. So if we get the question, we will address you.
Okay.
No.
We can choose these molecules for the folic acid, and then we go for single point energy. As sir told you, we have other options to calculate here, but due to time constraint, we are doing only single point energy. But in future, maybe we can add it. So we do the grafting, and for the folic acid, we'll upload the list file first, and then the XYZ file. After doing this, we will click on display options. Same goes for this. After this, you can see the 3D visualization of the molecules here. And after click, it goes same for this. You will click on fragmentation, and you can see here there are many more fragmented molecules. In the previous ones, you can only see 3. There are total 7. And after this, you do the same. You go to submit, and after submit, you go to execute job. So now you can see here your job has been submitted with the following input parameters. And now you go to empty home and check your job status. So these are the 2 jobs which we have submitted. This one is the ALA, and this one is the folic acid. So now we can check the status of these 2. So it will take some time to open.
Okay, here I want to tell you one more thing. Through the PES, the beauty of the PES is that this is a problem solving environment is taking the Cartesian coordinate from the user, calling the MTA program at the background, and it is submitting the jobs on the HPC machine. We are calling it a HPC Shivai, NSM machine, Param Shivai cluster. So at the back end, all your calculations, mean the calculating the single point energy of a molecule, two molecule, which is demonstrated here, they are actually get submitted on the Param Shivai machine, which is a supercomputer developed by under the NSM initiative. And the jobs is running on the NSM, and it is giving back the output to the user, and you can able to see it. So this is what this is a problem solving environment is doing. You need not to have to worry much about how to submit the job on HPC machines. In the backend, it is running actually.
You don't need login for HPC. You
Yeah.
need login of a PSE only. So you are using application only. So
As you can see here, your job is getting submitted. So it takes mostly around 5 minutes to go to the job to the HPC system, and then you gives you the output. So depends on the machine. So it will take some time. Then you will get your job. You can come and check your status. We have provided you with like the input files of three other molecules. So if you want, you can also do this, submit the jobs through that also, and come back here and do the same process. That you can check the job status through your own login pages. So you can check here. Once your job is completed, you, as I've shown you in the slide, it will give you that your job has completed, and then you can go and click on download output, and then you can see the output files. So we'll wait until the job is completed. Once the job is done, I'm going to show you how what is the output of 3 and 4. Our job ID, that is here 3 and 4, and you can see. So it takes time, maybe 5 minutes. So then you can download it.
so job number 3 and 4 are submitted to Param Shivai.
Yes.
Ashish,
Yes.
Pooja is suggesting, can you submit one more time because I think she missed somewhere.
Yeah, I can submit it one more time.
Yeah, yeah.
So here you can go to submit jobs, and after this I'm going to select the options. So MP2, so you can choose Dunning, and then this, and after this so you choose single point energy. From here you can choose grafting or non-grafting. After this you need to upload the fragmentation file. So we are doing for the ALA. So here we choose the fragmentation file first, and then we upload the input file ALA dot. So after doing all this, then you have to click on display.
There are two input
So
files.
yes. So after this, you will get the molecules here after filling all these values.
It's a 3D visualization.
Yes, it's a 3D visualization
You
molecules.
can see that molecule. properly. Just move it, Ashish.
Yes. These are the also the fragmented molecules. You can see it full 3D.
Here the blue balls are the nitrogen, the black one are the carbon, red is the oxygen, and the white is the hydrogen.
Okay.
Can you just go up? Go. Okay, so go up.
So this one.
Yes, fragmentation summary. It is okay. So it created this. These are the fragments.
Yeah.
Okay.
After go, you can submit here. This is a submit jobs page. And after this, you go on execute job.
This is the sequential version of MTA, which is submitted on Param Shivai through a queue called SSK.
Now I will see some what are the problems are coming.
Hello.
Hello. If anyone is having any problem, then my colleagues will try to solve it. They will email you how to connect with it, Pooja. So we will help you to connect, and then you can submit the job.
Okay. Meanwhile, I will show you the command line utility of our software. So.
Subodh,
Yes.
actually, Pooja has written one comment that
Sorry.
she is facing problem. Pooja,
Yes. Yes, sir.
she
We are
is
trying
facing
to solve.
problem to open the error.
Yeah, yeah.
Yeah,
To
I
open the
think
site.
that is.
I will call. I will contact her and try to solve her problems.
Okay, okay.
Subodh sir can show his command line, and I will try to contact her and then try to solve the problem.
Yes, yeah. Thank you.
Yeah. Nityananda, can you say share your screen?
Yes.
Yeah. Here we are first demonstrating how to use our software. And first, I will going to show you the single point energy calculation and followed by the frequency calculation for one of the job. And we are showing only the vibrational IR one.
Now is it visible?
Yes.
So, you want IR graft or MTA graft?
MTA graph, but first show open one of the XYZ file.
Yes. So we have a molecule known as alpha cyclodextrin that is optimized at certain level of theory. And this is the optimized geometry, which is containing 126 atoms. And the molecule is cyclodextrin. So this is the basic structure of XYZ. The first line is the number of atoms. Second line is anything, a comment line. and it is followed by the XYZ coordinates along with the symbol of the atoms. Okay.
Okay. And this again, these are the coordinates in angstrom. Okay. And MTA software will run only on the Linux platform. It is not available for the Windows version. So to use the MTA, you need a Linux platform and the Gaussian ab initio software at the backend. Okay. Now we will show you how to evoke the MTA architecture for this purpose. So when you are installed the Gaussian software, then you will get the one folder called as an MTA spec. Can you just show ls dot dot? Yeah, enter. Yeah, so there you can see there is one folder called as an MTA SRC. An MTA SRC, there is one file which is a driver script, and you have to evoke that script. So you have to first write a Python because it is a Python interpreter. Saupen, can you please write Python? Then you have to give the first command line argument as the MTA, go to MTA SRC and MTA.py. No, submit the job for FRGONL.
Okay. So now with the same fragments, or we will make some fragments for them?
Yeah, first one will show the utility, what it does. Okay, we already showed that we are fragmenting the alpha cyclodistinct molecule.
Okay.
Okay, and now we are generating the fragments for it, and you know how many atoms are there? 126. Okay, and after the fragmentations, after generating the fragments, so for generating the fragment, you have to use the file called as an param. And can you open that? And in that file, these are 5 user-defined parameters. First is the RDEXT, means this is the parameter associated with if you are already having a fragmentation scheme in your hand, you have to set this variable to true by setting it to the 1. Or if you want to the automatic fragmentation scheme, then you set it to the 0, means then the program will generate the fragmentation scheme for you. Now, as it is set to 1, we are using the already generated fragmentation file for this program. Then the second parameter is the addDum. AddDum is the parameter for asking basically indicating the program to add the dummy atoms or not. Because since morning you must have listened that this is a fragmentation based where we are cutting the molecules, single bonds. So if you cut the single bond, then the valency of the atoms will not satisfy. Then it will show a charge error. So to satisfy the valency for saturation, we have to add the dummy atoms. Dummy atom is a hydrogen to that. So if you cut any covalent bond, then you have to saturate it with the hydrogen, and this parameter is associated with this. If you are not cutting any covalent bond, then you may set it to 0. Otherwise, you have to set it to the 1. And the third one is the rad cut, which is used for generating the fragment size. Thumb rule is that bigger is the rad cut, bigger are the fragments, accuracy is good, efficiency is bit challenged. Then the third one is the max size and the mean size. Means if you are changing the rad cut is equal to 2.5, max size is 25 and mean size is 15, the system, the program, MTA program will try to fragment the molecule wherein one of the fragment is nearly equal to 25 in maximum size. It may slightly increase but not so very drastically, whereas all atoms in the systems are well preserved up to the 2.5 angstrom. So this is the general interpretation of these parameters, and you have to set this parameter before evoking the MTA software. Okay.
So to add that, so let's say you have a God given fragments in your hand, then this RDEXT should be equal to 1 because fragments are already given. And then once that is set as 1, then rad cut max size and min size has no meaning because you are already predefining the fragments. Okay, but when you don't have any fragments, you have to create first, then do the calculations. In that case, you put that 0 in place of 1, and then you can always control the size and the number of fragments by changing the value of the rad cut maximum size and minimum size. So right now we don't have to be worried because fragments are already with us, and this atom is 1 because you are cutting a bond while doing the fragmentation. Okay, so am I clear? Okay, so I'm coming out of this file. So what we need the XYZ coordinates of the molecule on which we are going to do the calculation. So this is the XYZ which I showed earlier. Now you are given a fragmentation scheme. That means we should have some information regarding the fragments, and that is all in this file, which is known as you see my XYZ file is alpha underscore cyclodextrin dot XYZ, and this is a key file frag.key. So the initials of both XYZ and the frag key file should be same. So up to this point, alpha underscore cyclodextrin, it should be same. In case of geometry, it is dot XYZ, and for the fragmentation details, it should be hyphen frag.key. So these two files we need. Okay, now what can we do? Since we have already the fragments, not the fragment inputs, but fragment data, we can now generate the fragment files in XYZ format and in frag list file. So for that, we have to run just the fragmentation module in the MTA spec. So we have written one script here to submit the data. So now you see there are three commands in MTA spec. One is frgonl, that is just to the fragments. Then MTA graft is for the single point energy calculation. And this MTA graft, if we replace this by IR graft, then that will the calculation will do the IR spectrum. And subsequently, we can do the Raman spectrum by putting Raman graft. So right now, since we are just about to see the fragment details, I am putting frgonl. Okay, now I can, and then okay, so now we can make the, see now if I do this one, only we have two files. One is the frag key and frag .xyz. Now I'm submitting a job, and the job submission type is for just fragmentation. So clear, yes. It is in queue. Try to is going to the queue.
Okay, can you show output file? Will explain meanwhile. Can you just open one of the file? Will explain what is it.
Okay, so these are all the files we get from the calculations. So I am opening the output file. If the job runs, then all these files will created. So okay, so this is the output file for alpha cyclodextrin for single point energy calculation. That is why the keyword written here is MTA graft. Okay, and if you see the fact forum, it is 1 because I use the existing fragmentation scheme. Okay, and this is 1, we are cutting the molecule. So MTA spec does means uses the grafting technology. That is why we have 3-step calculations or 3 number of calculations, 2 MTA calculations using lower basis and higher basis, and then 1 FC using the lower basis. Okay, so since we are interested in doing the getting the calculating the energy at B3 leap 631 plus Z double star. So this is my higher basis, and for the grafting procedure or the grafting technology, we used 631G basis set. So basically we graft from 631G to 631 plus Z double star. Okay, so we need 3 calculations and level of theory is B3 leap. So we have to do one MTA calculation at 631G and another MTA calculation at 631 plus Z star. And also we need a full calculation at B3 leap 631G level of theory. So this is what written here. First, what it does the full calculation at the lower basis. That means at B3 leap 631G level of theory, it will do a full calculation. Since we are doing B3 leap, so there is no correlation, so it is obviously 0. And this is the energy, which is the full calculation at the lower basis. Once the full calculation is done, then we have to do one MTA calculation at the lower basis again. Okay, so this is all about MTA calculation now. This is our input geometry. Then these are the details about the fragments and the atom details. And if you see, yeah, so we have 10 fragments for this molecule, having sizes 44, 44, 43, 43, 44, 44 again, then 242s, and then 243s. So these are the main fragments we created. And due to these main fragments, there will be many overlaps. Okay, the overall number of overlap fragments will be 32 minus 10, 22. So overall, we have 32 fragments. That means we have to do 32 calculations. Those are on the fragments. Okay, and if you see details of the fragmentation scheme again, it is all written in the out file. The total number of main fragments is 10. Number of overlap fragments is 22. So it is all total, it is 32. The average size is 43.20. This is the average size is defined only for the main fragments, because we do main fragments. Overlaps, they are automatically created. So the fragment size of the scheme means the average of the fragment sizes of the main fragments. So it is 43.20. The RG value, that is 2.68. And then this is scaling factor. I think right now we should not talk more about this, but these are the details about the scheme which we have used. Okay, now we have to do 2 MTA based calculations. One is at smaller basis and one is at larger basis. You see, we have 32 fragments. Then for each fragment, we have to do the MTA-based ab initio calculations. So we will get energies for each fragments. Then we patch. This is all automated, and these fragment energies will be patched by the cardinality based set inclusion exclusion principle to get an estimate for the full molecule, and we get this is the energy of alpha cyclodextrin from the MTA based calculation at B3 leaf 631G level of theory. That means MTA at smaller basis. Once smaller basis is done, then we have to do also the higher basis, because that at that basis we want our energy of the system. So higher basis means what is that? That is 63 plus 631 plus Z double star. Okay, so it will do the calculation at higher basis. So MTA based calculation, again it will do everything. It will read the geometry, then the fragment details, then it will summarize the fragment details, then it will do the calculation of on all the fragments, and then this will give the total energy, that is the MTA energy at the higher basis. So now we are done with the three calculations. FC at B3 leaf 631G level of theory, energy this one. MTA B3 leaf 631G, energy is this one. Now you see these two energies. They are not equal. They are differing in the second digit after decimal. Okay, that means the MT energy is in some error with respect to the full calculation. Okay, and then we have to take that error and add. So, and that error is known as now the correction at the smaller basis. So this is this one. This is simply FC minus MTA. You subtract the MTA part from the full calculation. Once you get this correction, you add that to the energy which you get from the higher basis calculation MTA. Okay, now you add this one, and this is our final energy. So this energy will be now our grafted MTA energy for cycloalpha-dextrin at B3 leaf 631 plus Z double star level of theory. Okay, so this is how you will get the final estimated energy, which is corrected through the grafting procedure. Is it clear to all? Okay, it is not coming. So what can we check with the Paramparul?
Yeah, but actually thing is that you just show the output of the IR now so that we will explain it instead of submitting the data.
Okay. Okay, so then we have another molecule which is known as 1CEK. It is actually a protein, a small protein containing 103 number of atoms. Okay, so for this we are going to get the IR spectrum. Okay, so if we are going to do the IR spectrum calculation in MTA spec, then our keyword should be IR graft. Okay, so this is our submission script. So we are interested in. So now this is our command line. We are doing the MTA based calculation. The input should be 1CEK XYZ. Output is 1CEK out, and this is IR graft. The keyword is IR graft means it will do the IR frequency calculation. Okay, so now
coordinates of alpha cyclodextrin 1CK and those molecules submitted by Ashish, these are already shared with you. You all also can check it out at your end.
Okay, now you can see the output file. Okay, so when you do a frequency calculation, I think you all know it will first do the energy. Okay. Then once you have energy, then it will do the double derivative energy, then Hessian, then frequency calculation. So while doing the frequency calculation, we will get the energy first, then the spectrum. That is why this is the end of the output file from the IR graft calculation. You see, it also tabulates the energy. So this is my grafted energy at 631 plus G star level of theory when we use 61G as a lower basis. Okay, so now this is all about energy, but what about the spectrum? Okay, the spectrum will be in 1ck-vs.log file. This is our output, which is written in a Gaussian format, which contains the data regarding your spectrum, intensity, frequency, and then all other parameters. Okay, now I can check this. Okay, so this is what this is the file which is generated from the MTA spec based IR calculation, and you all know this is just a Gaussian file. Okay, and then if I check, you see it's all coming here. Okay, frequency, reduced mass, force constant, IR intensities, etc. Along with these are known as your normal coordinates. You all know when you visualize through any visualization software which supports Gaussian output file, you can easily see the spectrum, and you can easily tabulate the peak intensities, peak values, etc. Okay.
Is anyone having any question? And the link provided to you, which contains the Cartesian coordinate of this file. And now you all can submit the job through PSE and wait for completion. Okay, and we will be around. If you are having any problem, please ping to us or let us know.
Into the queue. Why is it so? Okay, so I am stopped sharing my screen. Then I'm trying to submit a job in front of them in a other server. Once that is free, then I can share. Is it okay, Subodhaya?
Yeah, that is okay. And anyways, now main thing is that participants should actively submit the job and they should come up with the error or if they are having any questions.
Yes.
So Nityanand and me and CDAC team is available now for a discussion. And if you have any problem, please let us know. We all are here for you.
Hello everyone. I'm going to share my screen and you can see the jobs that I have submitted. It has been completed. So you can see here, these are the jobs 3, 4, and 5 I have submitted. This is the job ID 5. You can see the output here. It took 9.24 minutes to complete the job. And this is the job ID 4. It is also completed. Folic acid molecule. It took like 22.3 minutes to complete. That's why it took time. And this is our job ID 3. This one is the ALA molecule. This is also took 20.52 minutes to run. And so this is our 3, 4, and 5, the job IDs, and it the all the 3, 4th, and 5 job ID has been completed. And now if you want to download it, you can go and click on the download button. So it will go on in your, you can download all. Will take some time to download the output because the output is coming from the HPC system and then getting downloaded to your system. So it will take like half a minute or something like that, depending on the connection. So it will get downloaded and then you can see the page. So that's what I wanted to show you. This is the ALA molecule. This is the job ID like 5. So it ran on 9.24 minutes. This is the same molecule, but it took time. You can see the job 4 here. It is already completed and you can go ahead here and download it. So you can see the downloaded file here. I will show you what the output looks like. And the job 5 is also done. So we will download the job 5 also. This is the job 3. So here the job 3 also is completed and then you can download it. And here are your downloaded files. So this is the job 3 and this is the ALA molecule. So if you want to see it, this is the output file of job 3.
Ashish,
Can-
can you say is alanine dipeptide?
What, sir?
Can you say alanine dipeptide instead of ALA? I know
Oh,
it's hard, but you
well,
can
I
say
didn't
this.
know, sir. I didn't know the full form, so
And it's
that's
okay.
why
It's alanine
ALALA.
dipeptide.
Okay, so I didn't know that it's ALALA and diapeptide. So
Okay,
this
okay,
is
no
the
problem.
food file of ALANA diapeptide. So you can see here, it will also give you the date and time, and this is your full output file. This is also the details of all the things and how much time it took. It took 20.52 minutes, I think. And if you want to see the fourth one, this is our folic acid job ID. So I will also open this, and you can see here, this is one is our folic acid, and here also the output file. Here you can see it took like 22.3 minutes. So that's why it was taking a little bit of time to complete it. Depends, it mostly depends on the connection. If the system is connecting great, the job can also be done in like 5 minutes or 10 minutes. So depends on where you are and the connection. So it took 22.3 minutes. And now let's check. This one is ALA diapeptide molecule, and this one which I are also submitted. So I think this one took less time to complete and get you the output. So it took like 9.24 minutes and the output files. So basically, we just wanted to show you that in this, you just need to have that necessary XYZ files and the list files, and you go on and select what you want to calculate. And based on that, it will give you the necessary out files and whatever is your calculation, and then you can go ahead. You don't need to know the like basic parallel programming concepts. You can go through the PSE site and just submit your jobs. So now we have time. If you want to submit your molecules, we have given you the total 5 molecules, and check whether it's coming or your output is coming or not. And if you're having some problem, you can tell us and we will try to help you. So basically, it's that only. So you can try to submit the jobs, and if you cannot, then tell us. We will try to solve your problem. And it will take just some time to get you the output, like 5 to 10 minutes. So basically, you will get your output. So you can see here, I've submitted the job in front of you, and the out file is also generated. So you will also get your output files. So basically, it will take just some time. So if you want, you can submit the jobs and then tell us if you are having some problem. These are the out files and everything, as you can see. So if you are having some problems, you tell us and we'll try to solve it. That's all from my side. Thank you. Hello. If anyone is having any problem, they can tell us in submitting the jobs or anything. So we will try to solve the problem. They can write in the chat window. Hello. If anyone is having any problem in submitting the jobs or he cannot submit the jobs, then they can tell us in the chat window. We will try to help them to submit how to submit the job. Hello. We'll wait for 5 to 10 minutes. If anyone is having any problems in submitting the job, they can tell us. We will help you how to submit the jobs, and if you cannot download the outputs, we will help you to get that also. So we'll wait for more than 5 to 10 minutes, and then we will be done with our hands-ons.
Meanwhile, if anybody is having any questions, they can ask.
Yeah, is anyone having a question regarding the methodology of MTA?
So if there are no more questions, I hope you are able to submit the job and see the output. If there are any queries, you can
write us an email, contact us on discussion forum or the mailing list, or you can generate a ticket for the same. So I just would like to conclude the today's training program. So I would like to take a moment to extend my heartfelt gratitude to each and every one of you. Moreover, I want to acknowledge the unwavering support and expertise of our speakers, especially Professor Gadre, Dr. Subodh Khire, and Dr. Nityanand Sahu. Also, the CDAC team here, Mr. Kedar and Mr. Shankar and Ashish, who these people are tirelessly working from past 15 days to make this event as a success, and they are making sure you will have a good hands-on session and learning of this MTA software. I also would, and their passion for sharing the knowledge and empowering others has undoubtedly contributed to the success of today's program. I also encourage you to leverage the connection you have made today, both with your peers and with our speakers always. I request you to subscribe to the MTA mailing list. It will connect you to the people who are having the similar interest and the work in the same area, which may help you to get the right guidance, quick solution and information, and opportunities to collaborate also. In closing, I want to express my sincere appreciation for your active participation and enthusiastic engagement throughout the day. Thank you once again for being a part of this enriching experience. I look forward to seeing the impact of today's training reflect in our collaborative achievements. So thank you, all of you. We are just sharing we have shared the feedback form in the chat window. Kindly, I request you to kindly fill up the feedback form. And the participation in few days, we will share your participation certificate as well. So request to share the mailing list, and don't forget to fill up this feedback form, which will help us in further improvement of our future training programs. And yes, thank you once again. So anybody from the audience, if you would like to mention anything. Yes, Mr. Shankar, you would like to add anything?
No, madam. No. Just...
Anyone, if they would like to add anything? Dr. Subodh, Dr. Nityanand Sahu.
Nothing in particular from my side, but to the participant, only one message. Our software is ready, and manuals are also ready, and man is also ready. You can approach us for any moment. Thank you.
Yes, thank you so much.
Thank you all.
Okay. Thank
Can
you.
we leave this group now? Can I leave this meeting now?
Yes, yes.
Yeah.
Thank you.
Thank you all.
Thank you.
Thank you all.